Today I'm going to present our paper on larger scale graph processing, which is a collaboration work between Penn State University and Samsung Memory Solutions Lab. So graph processing is heavily used in many different applications, such as search engines, social media, recommendations and ads, and maps and navigation systems. And also, it has a number of other applications in scientific and machine learning applications. But larger scale graph processing is challenging because graph dataset size is usually very huge, and graphs with billions of vertices and edges are very common, which can account for terabytes of data. And typically, graph data is stored on DRAM memory and accessed there. But due to high cost of DRAM and also dramatic increase in graph dataset size, external graph processing is very desirable, where we can leverage popular NVMe SSDs, which have very lower price per gigabyte, and they offer good performance. Also, during the execution of graph algorithm, a lot of irregular accesses can happen. For instance, when a vertex wants to update or access its neighbors are not necessarily adjacent on the vertex list. And this results in many fine-grained and random accesses during the execution. And when storing all graph data on SSD, including vertices and edges, it can happen that these neighboring vertices of the blue one are not going to be necessarily on the same SSD page. And on the other hand, SSD page size and vertex update size don't match. These vertex values can be in range of several bytes. For example, the vertex value can refer to its rank in PageRank algorithm. But on the other hand, SSD page size can be several kilobytes. So now you can imagine when we want to update a value, a vertex value, we need to write the whole page. So, and writes in the SSD are usually slow. So that's why such vertex updates are detrimental to both the performance of application and also to the endurance of device, because as we saw in the first paper presentation today, each SSD page can endure only limited number of program erase cycles before it wears out. Okay, so prior work on external graph processing tries to resolve this issue by providing a perfect sequentiality for vertex updates. But in fact, if we could have all vertices stored on DRAM and access it there, then such fine-grained accesses was less of an issue. But when we're moving all the data to SSD and to be able to run the execute the graph algorithm with limited DRAM, then because of the mismatch between the size of SSD page and also size of these updates and their randomness, it is not directly feasible to do that. So prior work on external graph processing, which maintains all vertices on SSD, tries to achieve this perfect sequentiality in accesses by coalescing all these fine-grained updates and then applying it to SSD. So we take Graph Boost, which was recently published, as an example of state-of-the-art external graph processing framework, but the same arguments we make can be applied to other external graph processings where they also try to provide complete sequentiality. But before getting into details of how GraphBoost works, let's first talk about the programming model. So to enable parallelism when executing graph algorithms or running graph analytics on big data, they usually employ vertex-centric programming model, which is which works in an iterative fashion. And each vertex runs a user-defined program which depends on graph algorithm. Sometimes it can be very lightweight computation, for example, a summation or a minimum operation. And during the execution, each vertex sends the updates to its neighbors along the outgoing edges. This is a specific type of this model called pusher style, where each vertex pushes the updates to its neighbors. So now let's see how GraphBoost works. So first, graph data is represented by a set of vertices. For each vertex, we maintain its attributes like the ID of vertex and also its value. And also for each vertex, we need to figure out what are the neighbors of this vertex. That's why we keep pointers to the edge file to figure that out. So during the execution, vertex data is read from the vertex file, and then based on the index of its neighbors, we access its outgoing edges. And in this example, we have vertex V0 being connected to 3 other vertices, Vx, y, and z. So we have 3 edges here. And now V0 wants to send its value or its update to its neighbors. So the updates are generated in a key value form where keys are the ID of neighboring vertices or destination vertices, and the value is the value of V0. So the way GraphBoost, so as I explained in earlier slides, these updates can be to different and random locations in the SSD. So that's why GraphBoost first tries to sort all these key value pairs based on their key. But again, because the size of updates are very large, it's not possible to do it in one shot. That's why they split the data. They sort each part of data, log it on the SSD. Later on, they stream the sorted chunks and merge them together. And finally, write big chunks of sequential and large data on SSD. Okay, but this sorting, although it provides such perfect sequentiality to access SSD, it comes at a price. So we want to look at the execution time breakdown for GraphBoost running PageRank and breadth first search or BFS algorithm on different graph data. And we see that when looking at different parts of execution, like reading and writing vertices, reading edge from edge file, and also running graph algorithm, which I call it here edge program, and also the sort part, we see that the execution time that is spent specifically for this sorting can be sometimes significant. And in this example here, for PageRank algorithm running on WebGraph, it can take around 60% of execution time. And also, as you notice here, PageRank usually has higher overhead for sort because in each iteration it tries to run on all the vertices, and hence they generate more number of updates, which takes more time to sort them. We also want to investigate the scalability of GraphBoost by giving a simplified analysis of its execution time. So we can break down the execution into 3 different phases: reading from SSD, running graph algorithm, and then sorting in the memory and writing back to SSD. So reading and writing from and to SSD takes a linear time with respect to the number of edges in the graph, and sorting in the memory usually takes E log E time. So now you can assume, when assuming that DRAM is K times faster than SSD, we can see that when when the graph dataset size grows such that log of E becomes larger than K, then this sorting phase can actually be a bottleneck. To verify that, we run an experiment on different graphs with same number of vertices, but we increase the number of edges, what we call edge factor here, the ratio of edges to vertices. And we observe that when the number of edges are increased, in turn, the number of updates are increased, and then the sorting overhead, or the percentage of execution time spent for sorting these updates, is increased. Okay, so GraphBoost tries to sort all the data to provide sequential accesses. In fact, they are trading off more computation for better I/O accesses. But as we see here, their approach doesn't scale very well with increasing dataset sizes for graphs. So instead of doing that and coming up with completely sequential accesses for very large amount of data, we try to propose a partitioning mechanism for vertices in the graph to actually eliminate the need for such perfect sequentiality and also the sorting of updates. But partitioning in graph has been already studied in many different domains. Actually, perfectly clustering and partitioning graph data can be an NP-hard problem, but prior work come up with different partitioning for either whole graph data or just the edges to enable running graph algorithm on either in a distributed fashion or in a single machine. But all these approaches are actually not well suited for fully external graph processing, where all vertices and edges are stored in the SSD and only limited amount of DRAM is available. Because some of these works require all vertices to be present in the main memory during the execution. And on the other hand, some other instances, they apply their partitioning to whole graph data, including vertices and edges, and they do not decouple vertices and edges. And as a consequence of that, they need each partition, the data associated with each partition, to be present in the main memory to process that partition. And in the main memory or cache, and because of limited size of cache or main memory, sometimes the number of partitions can dramatically increase, which in turn can cause high overheads for cross-partition communication and or replication. So instead of that, we propose partitioning only for vertices in the graph, unlike prior work. And the goal of our proposed partitioning is to reorganize graph data such that vertices associated with each partition can fit in the available DRAM. And having a set of source vertices and set of destination vertices. So we take these destination vertices where actually the updates are going to happen to them, and we partition it such that each partition can fit in main memory. And When processing each partition, we need the source vertices to these destination vertices as well. We put them in another table, and we sort the vertices based on the vertex ID. I'll explain why we need it to be sorted later. And all this partitioning happens in pre-processing phase and doesn't affect the execution of the actual graph processing. And also for source vertices, we keep pointers to the edge file. Sorry. Okay. So here you can, because we partition the destination vertices, we want to preserve the uniqueness of destination vertices on their partitions. And to this end, you can imagine that a destination vertex can also be source vertex to others, right? So it can have some mirrors or copies of that on source vertex tables, right? So that's what I'm going to talk about next. To see later in this talk, I'm going to address how to update the mirrors to keep them consistent during the execution. But looking at the execution flow, first, all data is stored in the SSD. Destination vertices associated with a partition are read to memory. And next, we bring in the source vertex data. But this step can happen in a streaming fashion. This is where we can achieve parallelism when executing, during the execution. And this parallelism can happen for both vertex data and also the required edges. Okay, and then once we have destination vertices and source vertices based on the active list of vertices, we can access the required edges, bring them in the memory. So now, at this step, we have a set of destination vertices, all the source vertices to those destination vertices, and also we can figure out their neighboring information based on the edge information. And we can run the graph algorithm for this part. And hence, we can update destination vertices of this partition, which are already in the main memory. So once done, then to update the mirrors, we read the required metadata, and we generate the mirror updates, and finally we write all the mirror updates and also the destination vertices to the SSD. So next I'm going to talk about how these updates to destination vertices are happening in the memory. Okay, actually in this step we have a vertex list for which associates with a destination vertices of a partition, and we have multiple threads updating the elements of the same list. So now you can imagine that high overhead can occur because of to provide synchronization in the updates. So instead of doing that, we do apply the updates in two steps. First, each thread pushes the updates to larger buffers, each dedicated to a portion of vertex list, and later on, some writer threads pull the updates from these buffers and write them to vertex list. Okay, and also to update the mirrors, as I explained before, we need to read the required metadata from SSD. So this metadata is first for each vertex. We keep the ID of partitions where its mirrors belong to, and also for each partition, we keep the index of its mirrors on other partitions because we've already kept them in sorted fashion. We know that mirrors for partition I are going to happen before mirrors for partition I plus 1. This way, we can generate the updates, and it only takes linear time with respect to number of vertices. And the data, and this metadata is much, much smaller than graph size. It's almost negligible. Okay, in our experiments, our system is equipped with an Intel processor with 48 cores and has 256 gigabytes of DRAM, and we have 2 NVMe SSDs with 3.2 terabytes of capacity in total. We run PageRank and breadth-first search algorithms, and the input graphs that we study are web graph, Twitter graph, and synthetic graphs. So web graph is the largest available graph that we have examined, which has 3.5 billion vertices and 128 billion edges. And its text size of edges are around 2.7 terabytes. Okay, looking at performance evaluation, we compare our proposal, Vertex partitioning, or VPart in this figure, with software and hardware version of GraphBoost. So GraphBoost has a software version, and also they have an FPGA-based implementation where they offload the sort phase on the FPGA. But we don't have access to that FPGA implementation. That's why we extract numbers from the paper only for sake of comparison. And all these performance numbers are normalized with respect to GraphSoft. So the red line is GraphSoft, which is 1. And then the black bar is our proposal. We can see that sometimes we can get more than 2 times better performance compared to GraphSoft. And also, in many cases, we can see that we can almost capture most benefits of FPGA-based implementation, but without actually having any FPGA-based implementation. And interestingly, for large graphs like web graph and synthetic graph with 4 billion vertices, we can see that the performance benefits are higher. And also the space overhead for partitioning, because of the mirrors that the vertices have, account for 10% extra space overhead. Okay. We also report execution time breakdown, where we divide the execution time to I/O, memory, and mirror update. And we can see that mirror updates only account for 8 to 12% of execution time. And interestingly, I/O doesn't remain to be the main contributor to the total execution time. And sometimes it's more the computation and memory accesses which dominates the execution time. Okay, so I will conclude my talk that was about large-scale graph processing. We addressed the performance and scalability issues of prior work on external graph processing, and we devised this partitioning mechanism for vertices in the graph, which can be applied offline during the pre-processing phase to eliminate the need for sorting and providing perfect sequentiality. In the future, we are aiming to address dynamic graphs where they're evolving over the time. And also at the end, I would like to thank the authors of GraphBoost paper for their insights and help. Thank you. Any questions?
Okay, questions?
Peter Matsko from NetApp. I just want to get a little bit more of a clarification on your evaluation, because you said that, is it like 4 billion vertices?
Vertices, yeah.
And you said earlier you have 4 bytes. It's like typical Vertex data size.
No, that's for each vertex. So you have 4 billions of 4 bytes.
Right, so that's 16 gigabytes of Vertex data.
Yeah.
You have 256 gigabytes of RAM.
Yeah.
So why can't you just have a 16 gigabyte array in memory?
Yeah, so that's a good question. First of all, we to be consistent with Graf boost paper, we didn't use all the available resources like CPU cores and memory. We limited that to have a better comparison. And secondly, although for current graphs that we have studied, yes, that's right, they can all be stored on the main memory. But with graph data set size increasing, we can expect much more billions of vertices, which they can account for terabytes of data, and providing that much of DRAM can be costly. So this is kind of provisioning for this evolving size of graph data sets.
So you said then to how many gigabytes did you limit the RAM size for this evaluation?
For this evaluation, it's 128 gigabytes.
Yeah, but it's still like
yes, that's right. In this
but
the way we run the execution is that we have only vertices associated with each partition in the DRAM. But this is a very high-end system, right? If you want to run this algorithm on a low-end machine, then you won't have that much of DRAM. And because DRAM cost grows almost near exponentially, it's not always possible or cost-effective to accommodate all the data or vertices in the DRAM when executing graph algorithm.
All right, thank you.
Yeah.
In the middle, please.
Hi, Cornelius Curtis from IBM. Great talk. I have a follow-up question. So how would your approach compare to systems that have all the graphs, all the vertices in memory, like flash graph, for example, assuming that vertices fit into memory?
Right. So if we have enough memory to fit all vertices in the DRAM, all the vertices in memory, then we are not targeting that, right? We are targeting the situation where the size of vertices are actually very large that it's hard to fit all of them in memory. But I haven't run any experiments. In this case, the graph data, the vertices can fit in the DRAM memory, but I haven't run that experiment to compare with flash graph specifically. Maybe I can do it in the future. No, thanks.
Thank you.
Thanks.
Hi, Ren Shori from National Tsinghua University. Thank you for the talk. I'm interested in page 9, the bottleneck analysis of sorting.
Right. The performance?
This page, yes.
This page? Okay.
The red blocks mentions that if log AE
Log of number of edges.
larger than K, and K is the times the latency between.
So for instance, if DRAM is, let's say, 30 times faster than SSD, then if we have graph with 2 to the power of 30 or 1 billion vertices, 1 billion edges, this sorting can be a problem. This is actually very simplified analysis, so we can add more variables to it and make it more precise. This is just to give an idea of how this sorting can dominate the execution time.
Because it seems to me that K is roughly 1,000. So can you elaborate?
Yeah, K is solid, but E, the number of edges in graph can grow, right? When we have big graphs, the number of edges are very large.
It's hard to greater than 2 to the 1,000. The number of edge cannot exceed that.
Sorry, I didn't get.
2 to the 1,000 is a very huge number.
No, 2 to 30. So
2 to K, right? K is about 1,000.
Yeah, 2 to 30 is just a billion.
2 to 1,000 is a.
I'm saying 2 to the 1,000 because in typical systems, DRAM and SSD is a 3 order magnitude difference.
Yeah, but actually I extracted these numbers for NVMe SSD and typical DDR4 DRAM. Maybe that's for SATA SSDs. That can be 1,000, but in NVMe's are much more faster.
And can you elaborate more on the graph?
Sure.
Thank you.
So this graph has constant number of vertices, but we increase the edge factor in that. This is a synthetic graph, and we run PageRank algorithm on it. And the edge factor is ratio of edges to vertices, right? So when we increase number of edges, because the size of updates that are being generated are proportional to the number of edges, not vertices, we can see that when we have more data, more updates, it takes more time to sort them, right? And when we increase the edge factor, number of edges increase with same number of vertices, we can actually observe that in this figure, that the time that is spent only for sorting increases.
I see. So empirically, the latency of sorting can exceed, can reach about 70%.
60.
70. Okay,
Something.
thank you. I see.
Somewhat,
Thank you.
yeah.
So I do have a question.
Sure.
So it seems that the pre-processing that you're doing in dividing into partitions is actually pre-processing, right? So
It's done completely offline. Yeah.
right, it's done offline, but you have to do it, and if the graph actually changes as time
Right.
progresses, you have to do it over again.
Exactly.
So how much of an overhead would that be?
Sure. This is, in this work, we're addressing static graphs. And then, like I said, in the future, we're planning to extend our work to address dynamic graphs as well, where the graph data is changing.
Can you give us a rough estimate of how much this offline overhead would be? For your experiments?
Right, because it's done offline, I haven't worked, to make it perfect and optimize it because its execution time was not very important to me at the point. But if we optimize it, it can take several minutes or half an hour maybe to do that.
All right. Since we don't have any more questions, let's thank the speaker once more.
Thank you.